Thank you all, the GeoWomen of Calgary, for inviting me to speak. We're going to go for a ride into the future together, and it's not easy to see something that has never been before. That is where the futurists come in. For many years, I've spent 2 hours every morning scanning the world horizon for articles on real things that are happening today to address climate change, new technologies, new business models, policy, regulation, collaborations, commitments, plans, and patterns start to form up when you've been at it that long, and these can be projected into the future. So I run a daily blog called How the Future Can Go Really, Really Well. And originally it was designed as a homeopathic remedy for kids with climate anxiety, depression, and despair, so that they can hear about real positive events on which to base some hope. But I'm finding all manner of older general public people joining in as well. Even some of my technically oriented colleagues have subscribed to it. The website address is on the slide in case you want to sign up. I encourage you to join us. Take a photo of it if you wish. Right up front, I want to say that some of this material might be hard to hear. After all, our geology and geophysics livelihoods depend on how this energy transition shakes out. And I would say listen in the moment, take it in as a possibility without going through the rebuttals in your mind, because that's when we stop listening. There is power in entertaining a thought without accepting it. Any desirable future always starts with a clear vision of how we want it to look. Seneca, the Stoic philosopher from ancient Rome, I think it was like 44 AD or something, he said, if one does not know to which port one is sailing, then no wind is favorable. So you got to know where you're going. Let's start with a brief land acknowledgement. Oki, Abawashtech, Tatanastada, Tansi, Buju. Hello. My name is Maggie Hanna, and my family is of Irish and Scottish ancestry. We are 5 generations in North America, the first of us arriving on the Scottish side in 1884. And now we consider ourselves Canadian. We are grateful to be here on and with these lands, protected by the First Peoples for tens of thousands of years. I'm also adopted into the Roan family by my beloved sister, Moss Roan of the Ermineskin Cree Nation and Mountain Cree Camp. And for, I don't know, about 3 decades now, I guess. May we create space within our hearts and minds to listen and consider and humbly contribute to positive futures where all of us, including First Peoples, and all our relations walk together in a good way. Hydrocarbons are awesome. For the past 175 years, since the first steam engine was powered by coal in 1712, burning coal, oil, and natural gas have provided us with energy that is affordable, reliable, energy dense, easy to transport, and storable for seasons to years. And we have built our civilizations around them in this last century. The United Nations Sustainable Development Goals, all 17 of them, depend on number 7, which is affordable and clean energy. We have designed and built an ingenious hydrocarbon infrastructure systems to provide home heating and water purification and distribution, sewage systems, fueling stations for transportation, fuel for agricultural machinery to feed ourselves, to name but a few of the uses. And our human lifespans, health, and quality of life have increased because of hydrocarbons. But there are unintended consequences because we have been pooping the results of that combustion, the CO2, water vapor, and some methane off into the atmosphere ever since. So now we're being required to do things differently, to redesign our energy system so that we can get the services currently provided to us by hydrocarbons without the emissions. Energy transition is going to be messy. Why? Because there's a whole host of interrelated issues that need solving together, and some of them are listed here. Global warming of air and oceans, weather weirding and jet stream deviation. We're going to talk about that. Biodiversity loss, habitat loss, and maybe the start of a mass extinction. Plastics and microplastics in our air, water, soil, and bodies. Ocean acidification, because the ocean has been taking up a lot of CO2 from the atmosphere for us. Toxic chemistry in the air, water, soil, and our bodies. Waste management and mismanagement, I should say, of sewage, municipal solid waste in landfills, methane, air pollution. Reconciliation with First Peoples is key. Energy insecurity, food insecurity, and prosperity insecurity. And all of these things need addressing. And the thing is, many people consider and analyze these things in silos. We analyze new tech opportunities and applications, and without the holistic systems thinking required to put them together in a good way and considering all of the challenges that we are facing. Many solutions are overlooked because of this siloed nature within our companies, between industries, around politics, and geographies within countries and between countries. We need a broader outlook, I think, to actually see all these problems together and then apply really good, rigorous systems thinking to it, especially when we run economics. For example, in my work with startup companies, a couple of technologies might only be borderline economic on their own, but if we can combine them to solve bigger and more valuable problems, then each of them become more economic. Now let's turn our geological and geophysical eyes to look at climate change. Like it or not, the lion's share of human-caused greenhouse gases comes from burning hydrocarbons, 62%. And another 16% is due to methane releases from both hydrocarbon supply chains and agriculture. The average CO2 concentration over the past 800,000 years, roughly since the Middle Pleistocene epoch, has been 200 to 280 ppm. I was born at 315 ppm, and now today's reading is 422. That's a lot. Maximum so-called safe level is considered to be 350 ppm. So we have run out of and overshot the safe room in the atmosphere for more CO2. We've reached a planetary boundary. Yes, the climate has changed periodically over Earth's history, even before humans arrived on the scene. We geologists and geophysicists know this, and these have been caused by many natural factors, including changes in the sun itself, CO2 emissions from volcanoes, changes in the amount of land covered, meteorite impacts, and Milankovitch cycles. And so as a refresher, Milankovitch cycles describe how much solar radiation reaches the top of the atmosphere, Earth's atmosphere, and can vary up to about 25%. Milankovitch cycles depend on three things: the shape of the Earth's orbit, called the eccentricity, the amount of axis tilt or obliquity, and the direction in which the axis actually tilts, points, or its precession. And until now, through global climate change, though global climate change has typically occurred very slowly, over tens of thousands to millions of years, what we're doing now is geologically instantaneous, and we'll talk about that. And the general public might say, what does an increase in 2 degrees Celsius matter anyway? Well, it's not a big deal if the air around me is a little warmer, is it? Right? But that's weather. That's not climate. Climate is the average of all weather everywhere over the past 30 years. And we are sitting here at around 1.3 degrees Celsius of climate warming right now. It behaves like a constant fever. So if you had a chronic fever of 38.8 degrees Celsius or 101 Fahrenheit, you wouldn't be operating very well either. We geologists and geophysicists are the worst, though. Honestly, many of us are the educated climate change skeptics. And I think it's because we are trained to think in terms of millions of years. You know, I have a good idea, and I'm sure you do too, about what can happen to the Earth's surface in 10,000 years, or 100,000, or a million, or 100 million years. We know that the Earth's climate has changed many times and often drastically. Extreme climate changes have caused mass extinctions. We've identified 5 mass extinctions on the planet so far, all due to climate change. As an aside, I actually would say we've had 6 mass extinctions because I include the very first one in the Archean, when the methanogenic bacteria was the highest form of life, and it died out because some other upstart bacteria developed photosynthesis and started pooping oxygen into the atmosphere, which was poisonous to them. So, you know, it's happened before. The end of the Cretaceous was actually the only really sudden mass extinction. It took 15 years to kill the large dinosaurs. It was a result of a 10-kilometer diameter asteroid hitting the Earth over top of thick anhydrite beds. And it vaporized those anhydrites, putting the sulfur into the air so thick that almost all the sunlight was reflected back to space. Plants could not thrive then, so dinosaurs starved and died. Good news for us, though, is it opened the way for our mammal ancestors to evolve and thrive. And according to the fossil record, the other 4 mass extinctions took about 2 million years to accomplish. And recovery from all 6 mass extinctions back to a similar level of biodiversity took about 6 million years each time. 6 million years. So that's the time frame we're be looking at if we blow biodiversity. So now let's look at the geological time frame of the Quaternary period. Over the last 800,000 years, there were 8 glacial, interglacial periods during that time. And this graph from NASA shows them reflecting the Milankovitch cycles. The troughs show low CO2 in the atmosphere due to ice ages, right? Ices across the land. And the peaks are the higher CO2 concentrations during the interglacial periods when plants are more active, right, on the land. At the far right of the graph is a vertical line. It does not fit the pattern. This is our human-caused emissions, and the only vertical line on the entire graph. Notice the white horizontal dashed line marking the highest Quaternary CO2 peak of the last 800,000 years, which was 300 ppm. We blew past that in 1911. The vertical character of our line shows us a markedly increased rate of change over and above the Milankovitch cycles. This is geologically super fast, and rate matters. Why? Why does rate matter? Rate of climate change. Life can evolve and adapt to global warming if the rate of change is slow enough. Either that or it dies out, like the dinosaurs did, like the megafauna did in North America 13,000 years ago, when the climate changed too fast for them as we were coming out of the Laurentide ice age, right? Climatic zones are shifting. For example, forests can migrate depending on the species and where you are, how close to the equator you are, etc. But forests can migrate 15 to 500 meters a year, depending, right? But to outrun climate change, a forest has to move 3 to 5 kilometers a year. That's at least 10 times faster than they can. So global warming is changing the nature of nature. And the local circumstances and the weather patterns that we and all our animal and plant relations have become adapted to and are dependent upon are not as reliable anymore. And we only live because they do. The effects of global warming take the form of probabilities. There have always been extreme weather events. We know this as geologists and geophysicists. There are, but these days, more extreme weather is more likely to occur. And this comes from Carbon Brief, which is a UK group of data-driven scientists on climate change. And they concluded in a recent paper that today, 71% of extreme weather events are found to be made more likely or more severe by human-caused climate change, 71%. And at the same time, they say 9% of the time, extreme weather events were made less likely or less severe. So that's like 71 versus 9. That's a big deal. One of our biggest assumptions is that the climate emergency is an issue. It's not. It's an era. And that's because a lot of the ecosphere changes have already been baked into the system by emissions so far. So what global warming causes weather weirding through changing the jet stream. What is a jet stream anyway? Well, it's a fast-moving upper atmosphere ribbon of air at 9 to 16 kilometers above the Earth's surface that runs at speeds of roughly 325 kilometers an hour. And this affects things near the surface, such as the location and duration of high and low pressure systems, which shape the weather that we see on the surface. And today we're experiencing the tip of the iceberg of weird weather events and atmospheric heat and cold domes. And jet streams play a large part in the location and duration of those domes. Not long ago, the jet stream behaved like a fast-moving river you can see on the left here. Its morphology was more straight and smooth, and weather events moved through faster. Global warming causes more deviation in the position of the jet stream, bending it more north and south, like buckling it. You can see that on the right. So now weather systems can park over a certain geography much longer than before. Drier longer, wetter longer, hotter longer, colder longer than before. And as you can see from the diagram, the buckle up brings more hot equatorial air northwards. And an example of that was 2021 in Vancouver and central BC, when an 8-day heat dome caused 619 heat-related deaths just in Vancouver. It was humid and 34 degrees C at the same time in Vancouver. And in the interior of BC at the same time, it was dry and 50 degrees C, which led to the town of Lytton being burnt to the ground. So the buckle down then brings colder polar air southwards. An example of this was December of 2022 when Texas froze for 9 days, as temperatures were minus 15 to minus 30 Fahrenheit. They don't get temperatures like that usually, but for 9 days they did, and the power grid was knocked out. It wasn't designed for that kind of cold. Climate change effects take the form of probabilities. Yes, there have always been extreme weather events like droughts and floods and heat waves and extra cold winters and windstorms and forest fires. But I want to reiterate this now. We're looking at those things to a higher probability of them being more extreme and also more often. So How have we accomplished all of these emissions? As I said, today we rang in at 422 ppm of CO2 in the atmosphere. How do we get here? The short answer is progress with unintended consequences. And here's the Coles Notes version on this slide. We built the first coal-fired steam engine in 1712. In 1859, the first oil well in the world was drilled in Canada, in Ontario, actually, and the second one just across the border in the US, same year. By 1900, we had produced and burned 64 million barrels of oil worldwide. 64 million, not that much, really. The game changer of the Model T Ford happened in 1908, and then the watershed moment was in 1920, when huge Texas and Persian Gulf oil discoveries made liquid hydrocarbon fuels both abundant and now cheap. First oil sands leases were issued in Alberta in 1965, and now we produce 3.3 million barrels of bitumen a day. Today, our world oil consumption is 97 million barrels of oil per day. Total oil burned to date since its discovery in 1859 is 1,140 billion barrels of oil. That's a lot. Since 70% of every barrel of oil worldwide, and actually 78% of our oil from Alberta, is used for transportation fuel. And how are we going to decarbonize our transportation systems? By replacing fossil liquid fuel burning vehicles with battery electric vehicles, hybrids, hydrogen fuel cell vehicles, hydrogen internal combustion engines, hydrogen diesel biofuel trucks, air travel on SAF, which is short for sustainable aviation fuel, and or hydrogen, shipping fuels like ammonia, methanol, and also hydrogen fuel cells. Let's look at the history of just one of these things. Let's look at the history of battery electric cars, as they are really displacing oil demand these days. First, the first truly electric car was built in 1859, and same year as the first oil well was drilled, actually. In 1877, Nikola Tesla invented the first induction electric motor, which is used in Tesla cars and other electric cars today. Leap forward to the 1990s, when GM tested electric cars but dropped that experiment. In 1997, Toyota commercialized the first Prius hybrid battery electric plus gasoline. It was followed in 2008 by Tesla's first electric roadster. And a year later, the Tesla Model S hit the road. And then, a huge, world-shaking event. In 2016, I bought my used 2013 Tesla S85, complete with free supercharging, and I love it. World-changing event, at least for me it was. By 2017, 30 auto manufacturers in the world are making electric cars. And now there are 40 different electric cars for sale in the US alone, actually 80 models in Norway, because they have better subsidies there. In September of this year, 2023, the USA topped 1 million battery vehicles on the roads. And so in October of this year, Tesla dropped the price of a new Model 3 by 20% to $38,000 US, affordable and to beat out the competition. By Christmas this year, the US is on track to have 1.4 million battery electric vehicles on the road. And so the battery electric vehicle doubling time is currently about 14 months. That's fast. World passenger vehicle sales will be 70 million in total this year, and 14 million of those will be electric cars and plug-in hybrids. That grew 35% over last year. There are not many things that grow at 35% a year. So this is quite remarkable. So what else can we say about energy transition? Well, here are some principles. There's no such thing as more sustainable. Either it's sustainable or it isn't. There's no such thing as clean energy. Only energy sources with a lower life cycle greenhouse gas emissions than others. We have to maintain energy on demand while we go through this and do not allow our system to devolve into energy only as available. People suffer then. We have to electrify everything we can. We estimate Alberta's grid will need to be 2 and probably 3 times larger in supply and transmission to serve electric cars and heat pumps and other industrial things that are getting off, that are going to be using electricity. We have to reduce and then stop burning liquid fossil fuels for transportation, industrial scale heat, space and water heating. We have to convert the main grid to multiple yet connected MIDI grid systems, in my view. That's going to be the most robust when it comes to weather weirding, knocking out infrastructure. We also need to increase energy storage of all kinds and stop energy waste. Down. I tell you, there's currently 30% of the energy that goes into each of our homes is wasted. And not just our homes, our buildings, our businesses. You know, we do need a change in personal behavior. Another principle is to design for robustness, not just resilience. And this is a key in the increasingly weird weather world. Here's the analogy. And I would like to say that, you know, engineers are efficiency wonks, and bless their hearts, but efficiency isn't everything. Robustness is trumps efficiency, and here's why. Reptiles are resilient and mammals are robust. So reptiles are cold-blooded, calorie efficient. They need 1/10 the calories compared to a mammal. And they are so efficient, but they can only run fast for very short distances, and they die if the weather gets cold, too cold for them. Mammals, though, are robust. They are warm-blooded. They need 10 times the calories compared to a reptile. They are not efficient, but they can run fast for a really long time. Whether you're prey or you're a hunter, running fast for a long time is important for your survival. And mammals thrive well in cold weather. So resilience means that when a shock happens, we suffer and then we recover quickly. Robustness means that when a shock happens, we don't suffer, and the system in place easily handles that shock. So in a world of more extreme weather weirding, we need to build robustness into our systems. And on many levels of scale, from the single family dwelling or apartment to the neighborhood, to the city, to the region. What needs to be included in a robust, low carbon energy system? Well, here's one example of many. But all of them require backup power plants that kick in automatically using smart grid technology, which optimize low carbon emissions. That way, cleaner energy systems seamlessly switch from one power source to another as needed, from the lowest carbon footprint to the highest. So in this example, we start with solar power, which is intermittent. And when it's not on, then the batteries kick in. They're good for milliseconds of second support for the grid, but just for a short time, really. And then while they're kicking in, the stored hydrogen is fed into a solid oxide fuel cell to make electricity, and that has to warm up. So the batteries provide us a chance for that to warm up and work. And then when the hydrogen is tapped out, we switch to natural gas peakers which kick in. They have about a 10-minute warm-up time, the fastest ones do. And they have carbon capture on them as well. So I also think that demand response is something we're going to see in the electric pricing in Alberta and elsewhere. And in the not too distant future. So what is that? What does that mean? It's a voluntary electricity rationing that is accomplished by price incentives, offering lower power pricing in exchange for reduced power consumption at peak periods. So for example, as a family, you would not choose to run the clothes dryer during the 4 to 8 p.m. supper peak demand because it would cost you a lot under demand response pricing. Come on, baby. There we go. So let's take a moment and just say, this is my vision of the future, and I'm sure you could add a lot of things to this. What might the future look like by 2050? Well, we build our cities and infrastructure out of carbon. Circular economy is thriving. World population has stabilized. 50% of land and ocean is preserved and restored habitat for all our relations by 2050. As I said, we only live because they do. Mobility as a service in urban areas, so that's autonomous shared electric vehicle fleets. Therefore, we'll need 60% less roads at that time in cities. Urban forests for city shade and beauty and cooling will be abundant. City gardens for food security. No more one-use plastics, and great plastic recycling systems in place. Waste to power systems in place. Virtual power plants and connected mini grids. Capitalism has been fine-tuned to close the gap between rich and poor people and re-expand the middle class. And social values shift towards elegance over accrual of wealth. Elegance is an elegant life is a combination of beauty and simplicity and having time to do the things that you most love. And all kids get an education in their own unique design and know their life purpose and their life mission. That's my wish. So now you've had a taste of the future. Let's get back to oil. Today, 80% of the world is powered by hydrocarbons. So why is it so hard to get off fossil fuel burning? Because, as I said before, fossil fuels provide us with these services: energy density, ease of transportation, storage for seasons to years, reliability whenever we call on them, and they're affordable. So my question is to you to think about, how many human work hours of energy do you think are contained in a single barrel of oil? Go ahead, take a guess. Put it in the chat or tell your neighbor, or, all guesses are good. Assuming a desk job, the answer is 4,053, which is 2 years of 40-hour work weeks. At $15 an hour, that's $61,000. And we pay what? $100 for a barrel of oil? So that's why it's so hard to give up oil. We get $61,000 worth of work for $100. That's compelling. But we have to recognize that we are the dog. We consumers, world energy demand, we are the dog, and energy companies are the tail. It's not the other way around. The dog wags the tail. They'll keep producing whatever energy products people will buy. And what we want to buy is shifting towards decarbonized energy systems. Hydrocarbon producers are looking at the early stages of demand destruction as the world chooses something else. It's a quandary. right? How do we maintain energy security with hydrocarbons while we still need them? And at the same time, enable their demand destruction through our energy choices. Well, the risk, of course, is in the messiness of this transition. It's a both and thing. We consumers require viable, decarbonized, affordable energy options to choose, and we haven't built those out fully yet. And we require hydrocarbon-based products to ensure energy security until we can make that shift. We have to get the timing right. And if we don't get this right, what would happen in your house if hydrocarbons were prematurely withdrawn from your world? What would happen then? I know what would happen in my house. There's power in entertaining a thought without necessarily accepting it. So let's explore this uncomfortable thought. What if oil, gas, and coal are going away due to demand destruction? Let's start with coal. Coal, there's two kinds, thermal and metallurgical. It's thermal first. Thermal power plants have already been replaced largely, well, not largely because China is still building them, but have been replaced by natural gas. Here in Alberta, they have, and some countries, they've been replaced by nuclear. And that's a good thing, because it also puts an end to the coal pollution. In addition to the CO2, which are things like sulfur dioxide, nitrogen oxides, particulate matter, particularly hard on lungs, mercury and arsenic, that coal plants routinely put into the atmosphere and into the water, and that aren't good for anybody. Production from intermittent renewables like solar, wind, pumped hydro, etc., plus energy storage in the form of batteries or hydrogen are starting to take over increasing amounts of the power load. Coal for high industrial heat processes like glass, cement, ceramics are progressively going to hydrogen and electricity as well. Let's look at some examples. They are all switching from hydrocarbons to hydrogen and electricity. These are 4-article headlines to help us to get that this is really happening in the world today. Steel is going in the first one here. Steel is going hydrogen and electric arc furnace. Cement is going hydrogen with graphene additives. Ceramics is going hydrogen with heat pumps, and glass is going electricity plus hydrogen. So hydrocarbons for industrial heat is going away. Just as an example, metallurgical coal to hydrogen, Hybrid out of Sweden has solved that problem. Like when you have iron ore, it's iron and oxygen together. And in order to make steel, you have to get rid of the oxygen. So coal grabs the carbon in the coal, grabs the oxygen off the iron ore, and leaves the iron to be pig iron, and then poops the CO2 off into the atmosphere. But so we don't just need heat, we need a reductant, which carbon is in coal for steelmaking. But hydrogen does the same thing. It both supplies the industrial heat and reduces the iron oxide by grabbing the oxygen and makes water out of it. So Hybrid out of Sweden, featured on this slide, pioneered this process and with a pilot plant that started up in 2021, and it's spreading around the world now. It works like a hot darn. Next up, let's look at the demand destruction for oil. 70% of every barrel of oil worldwide is used for transportation fuels like gasoline, diesel, jet fuel, and bunker. And these are progressively and chronically being replaced. Why? Although we have reasonable ways to decarbonize industrial scale emissions, we do not have economically viable ways to decarbonize emissions from one car or one house. and in aggregate, they have a lot of emissions, all the houses and all the cars together. These need to be fueled differently. So gasoline and diesel are going battery electric, hydrogen fuel cell electric vehicles, hydrogen internal combustion engine vehicles, hydrogen diesel biofuels. Jet fuel is going to SAF, which is sustainable aviation fuels, defined as like drop-in renewable or bio-based, bio-derived aviation fuels, and also to hydrogen. And shipping fuels become ammonia, some natural gas with onboard carbon capture, hydrogen and methanol. The IEA has calculated we have enough oil already discovered to take us to 2050, and says we should stop exploring for more. And I agree with them, although even my very rough calculations I've done myself say that we'll probably be about 4 years short. So a couple more big finds wouldn't hurt. I bless you. Jet fuel, yeah, but no more, just a couple, no more. We, stop exploring. So jet fuel demand destruction. Let's look at this. Here's some real world examples replacing jet fuel. The very first zero emission plane in the entire world was designed and flown out of Canada. It was Vancouver's Harbour Air, and they built a battery, small 7-seater plane and flew it from Vancouver to Victoria. It was a small, plane, and we find now that batteries can be used for short hops, but not for long distances. And then Zero Avia was the next one, and they designed hydrogen fuel cell flight. And since then, many airlines have gotten into gear with decarbonized flight. And here are pictures of 2 of the many planes flying today on hydrogen: Airbus and Zero Avia. United is the one of the airline companies that's testing SAF, bio-derived sustainable aviation fuel. Now let's look at shipping and the demand destruction of bunker fuel. There are about 50,000 container ships in the world, and they move over 90% of the international trade goods. It will take some time to convert them all, but the conversion has already started. Here's some examples of alternative fuel ships in service today: an ammonia-fueled tanker, a methanol-fueled container ship, a hydrogen-fueled ferry, and an electric tugboat. So demand destruction for all liquid hydrogen fuels is underway. This is not pie in the sky. This is happening now. Now for a really important concept. We have to make a really clear distinction between the goal by 2050 and the pathways we need to get there. And they are different. We have to do things now that we won't be doing by 2050 in order to get there. And so we require hydrocarbons now, because we can't take a step from where we're not without too many people starving and freezing in the dark. So there's no question that we need to burn fossil fuels in the near future, because the energy transition can only be accomplished on the backs of those hydrocarbons, because there is nothing else. We can't make decarbonized consumer energy choices until we've built out alternative options that are dependable and affordable. That said, here's what I think is going to happen to hydrocarbon demand between now and our goal by 2050-ish. The black is coal, the oil is green, and the red is natural gas. Barring World War III or some such nastiness, which would boost hydrocarbon burning just for energy security purposes, we are looking at coal and then oil demand destruction first. Thermal coal peaked in 2013 already. Metallurgical coal use has plateaued, and in my guess, will start to decline in about 5 years. Oil demand is poised to drop, as discussed, and that leaves natural gas. I think the demand for natural gas in the short term to medium term is going to expand for 2 reasons. Number one is that natural gas has half the emissions of coal for the same amount of energy, so will continue to be fuel switched from thermal coal for power generation and other uses, industrial scale uses, and that there's a new technology. One of the companies that I'm working with, Rain-Cage Carbon, this technology was developed here in Calgary, and it enables us to take biogas and natural gas to become the hydrogen carrier of choice into the future, which is why I've drawn it leveling out higher than coal or oil. So that's right. I said natural gas will likely be the future hydrogen carrier of choice. And that's a bold statement. And here's why I think it. What if we could ship LNG, stands for liquid natural gas, to Japan, say, and they put it into a steam methane reformer, which makes hydrogen and CO2, and the hydrogen goes into the local gas grid for local distribution. And if we could grab over 90% of the CO2 out of that flue gas stream from that steam methane reformer and make valuable solid structured carbons out of it for sale into Japan's manufacturing sector, then that would be a low carbon hydrogen production system. Canada already has one LNG export terminal under construction in Kitimat, but we could use about 4 more. We have natural gas and biogas pipelines. They're the same. We have LNG ships that are common in the world. We know how to do this. According to the Canadian Gas Association, as of 2022, Canada is estimated to have 1.368 trillion cubic feet of natural gas resources. That's an amount equal to over 200 years of current annual demand. Rain-Cage Carbon, as I said, is a Calgary company, and they can facilitate this into a low carbon system. They've developed this radical new technology which can grab over 90% of the CO2 out of any industrial scale flue gas stream at any concentration between 2% CO2 and 70% CO2 for about 2 kilowatts of power, which is remarkable. It is a bolt-on unit, so it can be added to existing facilities as well as new builds. It outputs useful graphene family structured carbon molecules like multi-layer graphene, carbon nanotubes, and buckyballs by the tons a day. And we think at least 60% of the products we use every day might be improved by incorporating graphene family structured carbon molecules into them. Things like paints and adhesives and cement and strand board and building materials and car bodies and batteries and medical applications and many, many others. This tech is at technology readiness level 9, which means it's borderline commercial. It also means that we will be able to continue to burn hydrocarbons in industrial scale plants, emitting under 10% of the usual emissions. And this serves us well because the first half is, especially in the first half of this energy transition pathway, because we will not have to prematurely mothball existing plants and can use them to keep the lights on while we work to decarbonize energy systems. 90% emissions reduction might not be enough for 2050, but it will help us cut emissions while we get there. My friend Blair Aiken is the brains, the CEO at Rain-Cage, and he calls this process a gaseous electrochemical process. So instead of putting lots and lots of pressure and lots of heat together like we usually do, We manipulate voltage fields to create an environment. It's not a plasma, but it's an environment that allows us to manipulate the carbon emission stream. So it's new. It's something people hadn't really considered before, you know, because most of our processes, we throw a lot of heat and pressure at it. Well, this is the opposite of that. So as a form of carbon utilization, it's likely going to be about 10 times less cost than putting carbon into the CO2 into the ground. But we still have to put CO2 into the ground because that's something we can do immediately. In order for the rain cage carbon system to work, we actually have to build out a market for these molecules, and so they don't like stack up around the world. And here is rain cage. Next slide. So oil and gas industry really doesn't have a good pivot, good singular main good pivot, but there are many smaller ones. And here's a list of some of them. And these this is a partial list of the kind of work where our geological and geophysical and engineering skills will definitely be needed. Natural gas, biogas, to LNG ports, to methane pipelines will likely expand significantly. Asphalt will continue as is. Carbon building materials will grow. Petrochem and lubricants will likely stay as they are. Blue hydrogen will continue and expand. Natural gas peakers will continue and expand for the last resort power supply and grid balancing when needed. Geothermal will expand. Gravity wells will become a big thing for electricity storage and arbitrage in places like Alberta that has a lot of existing well bores. Salt cavern construction will increase for hydrogen storage. Hydrogen storage is going to be done, I think, in drained natural gas pools. I think that's a very real possibility. Natural hydrogen and helium exploration is underway and will expand. Lithium brines will need drilling, production, and reinjection. Exxon actually 2 weeks ago announced that they're going to start lithium production for EVs, and by 2027 in California, they have quite rich lithium in their brines. Biofuel refining will expand. Stopping natural gas leaks on the entire natural gas methane supply chain will hugely expand, I hope. Reclamation of tailings ponds, industrial refining and processing sites and well sites will hopefully increase. Critical minerals will expand. And I put carbon capture and sequestration in deep sea line aquifers will expand. And even though it's 10 times the cost of making structured carbon, we still need it now because it can be implemented earlier than, and it's going to take time to put the carbon market together. It can be implemented earlier, and time is of the essence. So, but even if you look at all of these things together, my guess is the oil and gas industry will likely shrink by about half by 2035. That's my prediction. Even so, the oil industry has largely stopped denying human-caused climate change is a reality we have to deal with. One can understand why they want to delay credible climate action as long as possible. It affects their bottom line. But with demand destruction looming, they have taken a page out of the Merchants of Doubt playbook, those whose spin doctors' job was to create doubt around tobacco. I'm just going to move this a little bit. There we go. 1 minute. So here are the current natural gas industry 5 main messages. Redirecting more responsibility. Gee, it's not our fault. It's the consumer. Emphasizing downsides and costs of alternatives. Surrender. We can't do anything, so we might as well give up. Here, like that. Good. The need to wait for technology on the horizon to come, and then we will act. And fighting climate change is a losing battle. We might as well give up. In a country like ours, in Canada, where we have a high standard of living, good, ubiquitous education, inventive innovation culture, we are perfectly placed to capitalize on solving our emissions problems and then prosper by selling those advances to the rest of the world. China's doing this really well right now, and we could too. Let's look briefly at 3 example technologies useful to the energy transition that you might choose one or more of these, or choose to participate in some of these in your own life. So this is remarkable. This is a home electrolyzer unit that just came out of Germany, November 2nd, 2023, just this month. And the company is called Home Power Systems, and their new Picea 15 kilowatt system uses surplus power from photovoltaic installations on your roof to produce hydrogen via electrolysis and stores it in your house on site. And it offers, then in the wintertime, you take that hydrogen, you reverse the solid oxide SOEC, you reverse that unit, and now it's an SOFC, so it actually takes hydrogen and makes electricity out of it. And it offers 1,500 kilowatt hours of hydrogen storage capacity on site. This is huge. This is 100 times what a typical home battery can store. So I want one. We'll see. I don't know what the price is yet. So basically in the summertime, the electrolyzer is in SOEC mode. It makes green hydrogen. It's stored on site. In the winter, electrolysis runs backwards, so hydrogen is converted to electricity for use when needed. That's how this works. I think it's brilliant. Virtual power plants. I love virtual power plants. I think this is going to be key around the world. Solartility is a Calgary-based company, and I'm working with on and they make virtual power plants for Alberta. And so their job is to aggregate and supply home-generated solar battery power to support the grid. And it works kind of like a co-op. So they will install solar panels, a battery, and an electric car charger at your home or your apartment for no upfront cost on a 20-year lease. Imagine that you do that and all your neighbors on the block do too. Together, you become a virtual power plant. You pay for your power on and the monthly lease fee, and together those two things are 30% less costly to you than you paid for electricity before. That's the guarantee. It could be more than 30% savings. But because when the grid struggles, it pays roughly 2.5 times more for the power than the price we buy it for. So when the power is drawn from all of these home batteries together, when the grid's struggling, then the extra money that's made goes into this power co-op against everybody's power bills. So that's quite remarkable. In fact, we've been doing a couple of houses as a pilot here in Calgary. And the one that's been going on the longest, it's over 20 months, maybe 24 months by now. But over the average of a year, this house has paid no money for its electricity because of its ability to sell power into the grid, more power than it at a higher price. and that's offset the power cost to zero for average over the year. Let's look at heat pumps. Heat pumps heat and cool your home using electricity. They are like a box that sits outside your building and moves heat around much like your refrigerator does. It doesn't create heat. And so because it doesn't, it's actually 4 times more energy efficient than your gas furnace or boiler. It runs on electricity. It cools your home in the summer by taking the heat inside your house and moving it outside. And it heats your house in the winter by taking heat, even though it's cold outside, there's still heat there, taking that heat and moving it inside your house. So cold weather heat pumps are good to about -30 Celsius. But having said that, I will still keep my home natural gas for emergency backup because it can get colder than 30 degrees C around here. So those are three things that I just want to tell you about, so you can see that we are moving forward in solving decarbonized energy systems. And here's my final thought. How happy are you in your work? It pays well. Oil and gas pays well. It supports our families. We're good at it. And it might be going away. And where's the friggin' gift in that? Well, here's a thought that I subscribe to, and that is that every single person on this planet is here for a reason, an intention, a purpose, a mission that's absolutely unique to you. And your life force is a powerful thing, right? What we put our life force towards expands in this world because we're feeding it. And what is life force? It's the sum up of your thoughts, words, deeds, inspirations, feelings, energy, gifts, skills, creativity, inclinations, all applied to your work. And whatever you focus that on expands, right? Because we're feeding it. I believe that people deserve to be personally fulfilled in their work. I believe it's not only possible to work in your passion, it's the most productive way to live your life. I believe a person deserves to be excited and enthused about going to work. And I believe work involves entirely too much of our life to be taken up by something that we're miserable doing. My definition of life purpose, which I got from my life mission teacher, Daniel Goodenough, is do the thing you most love in the place you most want to be, with the people you most want to hang with, and in the way that the world needs the most. These changes in our industry are coming. If you're lit up from the inside by your work and have deep satisfaction with the legacy your life force is feeding, well, good. Then you're on the right track and fight to stay there. But if not, then as Captain Jack Sparrow says, this might be the opportune moment to take up the practice of consciously exploring your own design, your own life purpose and mission. And that involves journaling on really good questions that reveal your innate nature and propensities to yourself. There's some really good books out there in the bookstores with useful questions. The power is in the question. Buy a beautiful journal and have at it, So commit to journaling every day or every second day or every week on some of these questions that you can build up knowledge about your own unique design. And once you've done that work, you'll be able to distill it into a single sentence of intention that rings truer in your heart than any sentence ever has. And only then does one start looking for the vehicles to start carrying that intention into the world. So here's your intention, and here's the vehicle that you've chosen for that work to carry, and that carries that intention into the world through that work. And you want that work to be in alignment with your life purpose intention. As my life mission teacher, Daniel Goodenough said, he said, the highest possibility of who we can become is found within us by actually taking that journey. And I wish that for everybody. I think that's a way of the future. So thank you for your kind attention. And I hope this information and these perspectives have been helpful, and just give it the royal flick if it doesn't work for you. If I was in a room with you all, I would say, let's get to some questions. This is recorded. So Maggie, Hannah, signing off. Thanks. Hope this has been helpful to you. Bye.